IOE 413 Muscle Force Prediction Study Guide. Now let's do part A of this problem. And we'll write A up here at the top just to remind ourselves that it's part A. Part A consists of writing down the moment equilibrium condition for this, assuming that the forearm here and the ball is static. So we have static equilibrium. That means that the sum of the moments has to be equal to 0. The moments for the convention we will have, and we will consider a positive moment as being a counterclockwise moment. Okay, so for example, the muscle force would generate a positive moment, and the weight of the forearm and the weight of the ball would create a negative moment. Okay, the other thing to notice about this is that we're going to take moments about the point of rotation of flexion extension of the elbow, and let's assume that the reaction force from the humerus onto the elbow passes right through the center of rotation, so the moment arm of R is 0. That'll come back as we write down the equation. The other thing to notice here, statement in the assumptions of the problem, is that G is 12 newtons pointing downwards, okay, and W is 20 newtons, the weight of the ball. Our sign convention is going to be that upward pointing forces are positive and downward pointing forces are negative. And so when we compute the moments acting about the center of rotation of the elbow, the center of mass of the forearm has a moment arm of 15 centimeters, and the weight of the forearm is pointing down, so it's negative 12 newtons. And then the ball has a moment arm of 30 centimeters times a force of negative 20 newtons, negative because it's pointing downwards. Now, the biceps force, F sub 1, is pointing up, so it's going to be positive. And the moment arm is 4.6, so 4.6 centimeters times F sub 1. And then the moment that's produced by the reaction force is moment arm of 0, because if you recall, I said that we were assuming that the reaction force passes through the center of rotation of the elbow, which is where we're computing a moment's about. So moment arm of 0 times, and R is pointing downwards, so negative R is equal to 0 for static equilibrium, because as you'll recall, static equilibrium, the conditions were the sum of all the moments are equal to 0. The other thing to notice here is that 0 times negative R is 0, so that goes away. That's very convenient in this problem. So that's the end of part A. So now let's do part B. I'll write it over here. Part B is solving for the biceps force F sub 1 in this figure. So what we should do is rearrange this so that we have F sub 1 on the left-hand side and everything else on the right-hand side. And so I'm going to do 4.6 centimeters times F sub 1. And I'm going to put behind that newtons because I want to keep track of the units here. And to bring everything else to the other side, these negatives will switch to positive, so we'll have 15 centimeters times 12 newtons, because we brought it from the left-hand side to the right-hand side, plus 30 centimeters times 20 newtons. And what we're going to just do is divide through by 4.6 centimeters. So we will have F sub 1, and that'll be in terms of newtons, okay, is equal to, multiply this all out on the top, and you get 780. And the units on this are Newton centimeters. Physics 240 would be proud of me for keeping all of the units as we go through the calculations. And it's divided by 4.6 newtons, excuse me, 4.6 centimeters. Okay, Physics 240, you would not be proud of me for making that little verbal mistake, but I wrote it down correctly. So it's 4.6 centimeters in the denominator. The numerator is Newton centimeters, so the centimeters cancel out. So our units at the end are newtons, and that's what we have over here. F sub 1, okay, is going to be the ratio of 780 to 4.6, which is 170 newtons. That's our biceps force for this single muscle elbow model. Part C wants us to add two more muscles, two synergistic muscles. And a synergistic muscle is a muscle that has a moment arm of the same sign. We had the biceps muscle. Now we add the brachioradialis that has a moment arm of 3.4 centimeters. And a brachioradialis that has a moment arm of 7.5 centimeters. Instead of using F sub 1 as a muscle force, we're going to change our notation slightly here for the answer. And we're going to use the amount of force that's generated by each muscle. For the biceps, it'll be X sub 1. Brachialis will be X sub 2. Brachioradialis will be X sub 3. And to write down our moment equilibrium conditions, we will have 4.6 x1. That should look familiar from the previous part. The previous part, I'd written it down with the moment arm 4.6, but in the diagram I had F1, so I wrote down F1. Here we're using x1, so I'll do 4.6 x1 plus 3.4 x2, 3.4 centimeters times x2 force, and then plus 7.5 centimeters times x3. Now we have what's going on the other side of the elbow, which was our 15 centimeters times negative 12 newtons of force plus 30 centimeters times negative 20 newtons for the ball. And remember, we had plus 0 moment arm times the reaction force, and that goes to 0 right there. You'll notice that I am now becoming a bad boy in Physics 240 terms and dropping the newtons and centimeters. We're doing everything more like a math programmer here. We're worried more about x1s and scalar quantities here. Let's rewrite this down here as 4.6 x1 plus 3.4 x2 plus 7.5 x3, and then bring all this stuff over to the right hand side, and that's 780. And that is the algebraic description of our moment equilibrium conditions, in a term that sort of form that math programmers like to talk about. They like to talk about x's, you know, on the left hand side, and a constant on the right hand side. Let's do part D. Part D asks you to write an optimization model for predicting elbow muscle forces based on this mechanical analysis that minimizes the sum of muscle forces. So it makes the assumption that the central nervous system is minimizing the sum of the muscle forces, x sub 1 plus x sub 2 plus x sub 3, such that our moment equilibrium condition is satisfied. 4.6 x1 plus 3.4 x2 plus 7.5 x3 is equal to 780, and non-negativity applies to our decision variables because muscles only generate tension, they don't generate compression. That's just a physical fact of how muscles work. So this is our linear program for predicting muscle forces in this problem. Part E. This problem wants you to compute a candidate solution by allowing only the muscle with the longest moment arm to produce force. Set all other muscle forces to 0. Well, we denoted the muscle forces as x1, x2, and x3. The muscle with the longest moment arm is the brachioradialis, and that has a moment arm of 7.5, which is greater than 3.4 or 4.6. So we'll set x1, x2 equal to 0. So the problem says x1 is equal to x2 is equal to 0, and solve for x sub 3. And if we write in the moment equilibrium condition, it's 4.6 times x1 plus 3.4 x2 plus 7.5 x3 is equal to 780. Well, if x1 is equal to x2 is equal to 0, that's 0. That's 0. So we have 7.5 times x sub 3 is equal to 780. So x sub 3 is equal to 780 over 7.5, which is 104 newtons. And that's the answer to part E. Part F. Part F asks, is the vector of muscle forces computed in part E a basic feasible solution? If so, why? Let's recall that vector we just computed in part E was 0, 0, 104. We need to consider the system that is moment equilibrium, AX equals B, and muscle forces are non-negative. Well, in order to do that, we need to define A, which is the row vector of moment arms, 4.6, 3.4, and 7.5, and B is 780. To answer this part F, we need to determine whether X, this column vector X, is a solution to the system. Does it satisfy AX equals B? Is it feasible? That is, X is greater than or equal to 0. And the third part that's required for it being a basic feasible solution is we look at the columns of A that correspond to non-zero entries in X. And that set of columns of A that correspond to non-zero entries in X has to be linearly independent. If it is, then X is a basic feasible solution. To test whether X is a solution, we just determine whether AX equals B. So let me write down here, we're looking to see whether X is a solution. So we do 4.6, 3.4, and 7.5 times the column vector X, 0, 0, 104. And 0 times 4.6 plus 0 times 3.4 plus 104 times 7.5 is 780. Check. It's a solution. Is it a feasible solution? Well, let's check to see whether our vector X is in fact greater than or equal to the 0 vector. Yes, yes, yes. Check. So now we've determined that X is a feasible solution. The last thing we have to do is to check the basic part of this. For the last part of F, let us write down A which is 4.6, 3.4, 7.5. And then below it, write down X transpose. So we can line up the X's right below the corresponding A components. What we need to do is note the columns of A that correspond to non-zero elements of X. And that would only be the last one. So when you look at the columns of A that correspond to non-zero elements of X, you have the set that consists of the column 7.5. I mean, this is basically almost trivial. So then the question is the set of columns of A that correspond to non-zero elements of X linearly independent? Well, we only got one, so we'll see the question is 7.5. We'll create some new variable, call it y, equal to 0. What's the solution to this? Well, the solution is only y equals 0. The only solution to that is y equals 0. Therefore, the set of vectors in here is linearly independent. The set of vectors that correspond to columns of A that correspond to non-zero elements of X is linearly independent. And therefore, X is a basic feasible solution. End of part F. Part G involves formulating the dual of this linear program. Well, let's do our 6-step process. Okay, so step 1 is creating what I call the pseudo matrix form of the problem. So that's min z is equal to a row vector of 3 ones times x. And then our constraint will do 4.6, 3.4, 7.5 lined up underneath the cost coefficients times x is equal to 780. And then x1 is greater than or equal to 0. x2 is greater than or equal to 0. x3 is greater than or equal to 0. So that's step 1. Step 2 is associating a dual variable with the constraint. There's just one constraint. We'll make a dual variable pi. We don't need to subscript it because there's just one variable. We'll call it pi. And after that, let's do step 3. We can do 3 steps on this page. Problem is small enough. Step 3 is creating the dual objective function. Well, since we have a min, our dual will be a max. Let's say v is equal to, and then the objective function is the right-hand side times the dual. So that's 780 times pi. And notice here over here, just to remind you, that actually pi is written beside 780. It's not 780 times pi here. In the pseudo-matrix form, we just write the dual off to the side. Okay, but over here in the objective function, step 3, it actually is 780 times pi. So now step 4 is making the dual constraints. And I have the pseudo-matrix form written over here. And the first dual constraint is driven by the coefficients here in the red box that I'm making. The value is associated with x sub 1 in the primal. Okay, and what we have here is it's going to be 4.6 times pi. Pi is the dual variable associated with this constraint, right? Okay, so 4.6 pi, and then the right-hand side we have the corresponding coefficient of the objective function, 1 on the right-hand side here. Now the question is, what sort of sign restriction do we put in here? Greater than or equal to, less than or equal to, or equal to? Well, this is a minimization problem in the primal. And our decision variable associated with this dual constraint, the primal decision variable, x sub 1. Okay, if we come down here, it is greater than or equal to 0. You see it's greater than or equal to 0. Then we come across this table to the other side, and we have a less than or equal to form. So that means it is less than or equal to. That's our first dual constraint. Well, the second dual constraint is 3.4 times pi. We have 1 on the right-hand side from the objective function there, because we're looking at the second column. And we have the same process. It's a minimization problem. We go down the column. We get to the non-negativity restriction on the corresponding primal variable, x sub 2. It's greater than or equal to 0. So we have a less than or equal to form. The third dual constraint is going to be 7.5 times pi. Right-hand side is 1 again up here. Same story. We have a minimization problem. The corresponding primal variable is greater than or equal to 0, so a minimize problem. Greater than or equal to 0 for the decision variable. We go over to the side here and we get a constraint that's less than or equal to. And these are our 3 dual constraints for the problem. Step 5 of the 6-step process is figuring out the sign restriction on the dual variable. Well, pi is associated with that primal constraint. Let's look at our primal dual grid. Our primal problem is a minimization problem. Let's go down this column until we get to the constraint of the right form, which is equality. Go over to the left. We see that our variable is unconstrained, so that means that pi, our dual variable, is unconstrained, or we'll write it as u and r for unrestricted, and that's the sign restriction, or I should say lack thereof, for our dual variable pi. Now we can write down the final answer for part G. We have a maximization problem of v is equal to 780 times pi, such that 4.6 pi is less than or equal to 1. 3.4 pi is less than or equal to 1. 7.5 pi is less than or equal to 1. And pi is unrestricted. Now we can do the 6th step of our process. You'll recall step 6 is doing some simple checks. The first simple check is that if you have a min primal, the dual is a max. Well, the primal is a min, so we have a max. Check, that's okay. The second easy check you can do is make sure that you don't have any of your primal variables listed in your dual. The primal variables were x. Don't see any here, so that's fine. Check. The third thing we can do is to make the dual of the dual, and should be the primal, but I'm not going to take another half hour of your precious time to do that. If you want to do that, and it's a good exercise to do it on your own. So now we can do part H, which wants you to solve this dual by inspection. Well, that's pretty easy. Let's just rearrange these constraints a little bit by dividing through by the left-hand side. So the first one is going to be pi is less than or equal to 1 divided by 4.6. Second one is pi is less than or equal to 1 divided by 3.4. The third is pi is less than or equal to 1 divided by 7.5. And pi is unrestricted, so it can be anywhere on the real line. And we're trying to maximize an objective function that has a positive coefficient in front of pi. So we're basically trying to maximize pi, right? So the most restrictive one of these constraints is the one with the smallest value on the right-hand side, and that would be the one that has the largest denominator, right? So that would be this one. Pi is less than or equal to 1 over 7.5. So what that means is that the optimum solution to this problem is pi is equal to 1 over 7.5. And that's approximately 0.13. But we'll write it as a fraction here. 1 over 7.5. Part I. This wants you to show that the candidate solution computed in part E and the corresponding dual computed in part H are optimal to the model. Well, to show that, we need to show that ax star equals b, x star is greater than or equal to 0, pi star transpose A is less than or equal to C transpose. And then C transpose X star is equal to pi star transpose B. So these first two are primal feasibility, this is dual feasibility, and this is strong law of duality. We just need to show that pi star and x star satisfy these conditions. Ax equals b is true if and only if 4.6, 3.4, 7.5 in a row vector times 0, 0, 104 is equal to 780, and it is, so check. X is non-negative, is true if and only if we have 0, 0, 104 is greater than or equal to 0, 0, 0. Check, that's true. Now, dual feasibility. Okay. Let's put some stars up here just for notational consistency. So we have pi star transpose A is less than or equal to C transpose is true if and only if 1 over pi star, which is 7.5, times 4.6, 3.4, 7.5 is less than or equal to 1, 1, 1. Well, let's just multiply through both sides by 7.5. So then that gives us 4.6, 3.4, 7.5 is less than or equal to 7.5, 7.5, 7.5. Oops. Well, 4.6 is less than or equal to 7.5, check. 3.4 less than or equal to 7.5, check. 7.5 is in fact equal to 7.5, but that's less than or equal to, so that's check. So all of that is true. Lastly, we want to check that C transpose X star is equal to pi star transpose B. And that's true if and only if we have 1 times 0 plus 1 times 0 plus 1 times 104 is equal to 780 times 1 over 7.5. And that's true. So we've shown that our candidate solution satisfies primal feasibility, dual feasibility, and strong law duality. So our candidate solution of x star and pi star is optimal. Part J. Part J wants you to change the objective function to be the minimization of the maximum muscle force. Then convert this to an equivalent linear programming model. Well, let's write it down. It instructs us to, as we want to minimize the max muscle force. That'll be over the set x1, x2, x3, such that 4.6 x1 plus 3.4 x2 plus 7.5 x3 is equal to 780. Aren't we getting tired of writing the same equation down over and over again? And x1, x2, and x3 are non-negative. Okay, it wants us to take this optimization problem, which is not a linear program, and turn it into a linear program. The way to do that is to introduce a fourth decision variable, x sub 4. And now we write down minimize z is equal to just x sub 4, this new decision variable, such that x sub 1 minus x sub 4 is less than or equal to 0. X sub 2 minus x sub 4 is less than or equal to 0. And x sub 3 minus x sub 4 is less than or equal to 0. These are all constraints that just basically make x4 an upper bound on our variables 1, 2, and 3. And then we put down the same old boring constraint, 4.6 x1 plus 3.4 x2 plus 7.5 x3 is equal to 780. And now what we write down here is x1, x2, x3, and x4 are non-negative. This is a linear program that gives a solution set that's equivalent to the optimal solution set for the problem above. Now what you've been waiting for a long time, the last part of this problem, part K, which says analytically compute the optimal solution to the model developed in part J. So the thing to observe here is that when you do this minimax formulation and you're minimizing the maximum, you're minimizing x sub 4, it's basically going to come up with a solution that has an equal value for x1, x2, and x3. If any one of x2 or x3 is greater than the others, then x4 is going to be greater than it has to be, and x4 could be lower by creating more equality between x1, x2, and x3. So with that sort of arm-waving argument, we can say that x1 star is equal to x2 star is equal to x3 star is equal to what we'll call I star. One value. And we'll substitute I star in to this moment equilibrium condition, so we get 4.6 I star plus 3.4 I star plus 7.5 I star is equal to 780. If we just collect our terms here, 4.6, 3.4, and 7.5, we get I star is equal to 780 divided by 4.6 plus 3.4 plus 7.5. And that is 50.3 newtons. Now, I've conjectured with an arm waving argument that this is the optimum solution, okay? And since x1, x2, and x3 is equal to I star by our conjecture, we would say then that x1 star is equal to x2 star is equal to x3 star equals I star, which is 50.3, and this would be 50.3 newtons. Now, it will be a good exercise for you to go back and show that, in fact, this candidate solution is, in fact, optimal to this linear program without arm waving. And you know how to do that. You need to construct the optimal dual solution. Then you need to go through and check primal feasibility, dual feasibility, and strong law of duality. And I will leave that for you to do in preparation for an exam, because that's the kind of devious question that I might put on an exam. So with that, this very, very long problem has come to an end, and we're done.